Hello guys, this is Peter Mjali. Welcome to isinamuvatutoring YouTube channel. Please be sure to subscribe, like and share so that you don't miss any of our weekly uploads. In this video, I'll be taking you through work, energy and power physical science grade 12. I hope you enjoyed this video and find it helpful. Work measured in joules. Work is a scalar quantity which can be simply defined as an action done on an object that displaces the object, say from point A to point B. So for a work to be done, there must be a change in object's position. When there's no change in object's position, no work is done or 0 joules of work is done. When there is change in the object's position, there is work done on that particular object. Mathematically, the work done on an object by any force can be written as W equals F delta X cosine of theta. W being the work done on an object by a force measured in joules. F is the force doing work measured in newtons. Delta X is the change in position or the displacement measured in meters. And then cosine of theta or angle theta is a direction or an angle from the horizontal. Being able to draw a force or free body diagram is very vital in this chapter, so please make sure you are able to identify the forces acting on an object. Now, depending on a number of forces acting, we can have the work done by applied force being WFA equals FA delta X cosine of theta. The work done by frictional force being WFF equals FF delta X cosine of theta. FG, the work done by FG being WFG equals FG delta X cos theta, and so forth. But remember, FG equals mg, so the work done by gravity is WFG equals mg delta X cosine of theta. Now, the work done by normal force in this chapter is always 0 joules, because the normal force by definition is the force that acts perpendicular to the surface, and mathematically speaking, perpendicular is 90 degrees. So the normal force creates an angle of 90 degrees, and cosine of 90 degrees is 0, making the whole expression 0. Also, the work done by gravity is 0, but only on the horizontal surface. Remember, the force of gravity also acts perpendicular to the surface on the horizontal surface, making the angle of 90 degrees as well, as you can see on the diagram alongside. Now, when you add the work done by force number 1 and the work done by force number 2 and the work done by force number 3, depending on a number of forces acting, you're gonna get the total work done or the work net. Also, work net can be F net delta X cos theta, because calculating work net is more like calculating the work done by the net force. Okay, remember the net force can also be written as the sum of the forces acting on an object, meaning force number 1 plus force number 2 plus force number 3, depending on the number of forces acting as well. So that's why the work net or the total work done can be F net delta X cosine of theta. I'm sure most of you are able to identify the force acting and delta X from the given statement. The problem is identifying theta for each and every force acting on an object to calculate the work done by whatever force acting. So I'll be taking you through the process of identifying theta. I'll be using a cast diagram from trigonometry to identify theta for each and every force acting on an object. So on our cast diagram, the object is always at the center. The direction of motion is always to the right, horizontally, regardless of whether the object on the given scenario was going to the left or to the right, or the object was going up the incline or down the incline, or the object is being pulled to the right at an angle or being pulled to the left at an angle, or the object is going down vertically or going up vertically. On the cast diagram, the object is always at the center, moving horizontally to the right, as you can see the direction of motion there in the cast diagram. Okay, let us do a few examples on identifying theta, starting with theta for applied force. So in this scenario, an object is going to the right, the applied force and the direction of motion are to the same direction to the right. So going to the cast diagram, the object is at the center, always moving to the right horizontally. So on the cast diagram, we have already decided on the direction of motion. The direction of motion is to the right. Now on our scenario, the direction of motion and the applied force were to the same direction, meaning even on the cast diagram they must be to the same direction, meaning the applied force is also going to the right. As you can see on the scenario, applied force is horizontal, so even on the cast diagram the applied force is horizontal, going straight to an angle of 0 degrees. So theta for applied force in this case is 0 degrees. The work done by applied force is WFA equals FA delta X cosine of 0 degrees, the one we got up there. Even when the object is going to the left, the direction of motion in the given scenario is to the left. The direction of applied force is also to the left. Direction of motion and applied force are parallel. So taking the object to the cast diagram, the object is at the center, going to the right horizontally. So you could see on our scenario that the applied force and the direction of motion are to the same direction. So even on the cast diagram, they must be to the same direction. So because we had already decided on the direction of motion, the applied force must be to the same direction as well. So the applied force is to the right, going straight to an angle of 0 degrees, making the work done by applied force WFA equals FA delta X cosine of 0 degrees. Now the object is going up an inclined plane. The direction of motion is up the incline. Also the direction of applied force is up an incline. Taking the object to the cast diagram, the object is at the center, going to the right horizontally. As you can see, the direction of motion. So now going back to the scenario, the applied force and the direction of motion were to the same direction, meaning even on the cast diagram they must be to the same direction. Applied force and direction of motion were parallel, meaning even on the cast diagram they must be parallel. So applied force is going straight to an angle of 0 degrees. The work done by applied force is WFA equals FA delta X cosine of 0 again, the one we got up there. Another scenario, an object is going down in the inclined plane. Direction of motion is down, direction of applied is also down. So the applied force and the direction of motion are parallel and to the same direction. Even on our cast diagram, they must be parallel and to the same direction. But remember, we had already decided on the direction of motion. The direction of motion on the cast diagram is always to the right, horizontally. So the applied force is also to the right, horizontal, because they were parallel on the given scenario. So the applied force is going straight to an angle of 0 degrees. The work done by applied force is WFA equals FA delta X cosine of 0 degrees. However, theta for work done by applied force is not always 0. On previous scenarios, we've been getting 0 for the work done by applied force. That doesn't mean theta for applied force is always 0. Like the following scenario, an object is being pulled at an angle of 20 degrees. The direction of motion is to the right. The direction of applied force is to the right or somehow to the right. Although the actual direction is not east, but the direction is somehow to the right. So meaning the direction of motion and the direction of applied force are to the same direction, if I can say. So on the cast diagram, the object is always at the center, moving to the right horizontally. The applied force, however, is no longer moving to the right horizontally because now the object is being pulled at an angle. So applied force is going straight to an angle of 20 degrees, making theta of 20 degrees for the work done by applied force. So the work done by applied force is WFA equals FA delta X cosine of 20 degrees. Even when the object is going to the left, just like the scenario over here, the object is being pulled to the left at an angle of 30 degrees. The direction of motion is to the left. The direction of motion and the applied force are to the same direction, going to the left side. On the cast diagram, remember, they decided motion is to the right. So even the applied force must be to the right, because on the scenario, both applied force and direction of motion are to the same direction. However, the applied force is at an angle of 30 degrees, meaning the applied force is no longer going horizontally, but at an angle of 30 degrees. So the work done by applied force is WFA equals FA delta X cosine of 30 degrees. Now the object is going up vertically. The direction of applied force is up vertically. Direction of motion is up vertically. Both the applied force and the direction of motion are parallel. Even on the cast diagram, the applied force and the direction of motion are to be parallel. But remember, we had already decided on the direction of motion. The direction of motion is to the right and is horizontal. So making the direction of motion and the applied force parallel on the cast diagram, the applied force must also be parallel. So the applied force is going straight to an angle of 0 degrees. The work done by applied force is WFA equals FA delta X cosine of 0 degrees. Another case, the object is going down vertically. Direction of motion is down vertically. Direction of applied force is down vertically. Both the applied force and the direction of motion are to the same direction. Going to the cast diagram, the object is at the center. Direction of motion is to the right. Remember, on the scenario, the applied force and the direction of motion are both to the same direction and parallel. So make them parallel and to the same direction even on the cast diagram. So applied force is going straight to an angle of 0 degrees. The work done by applied force in this case is WFA equals FA delta X cosine of 0 degrees. So in conclusion, it doesn't matter whether an object is going to what direction. On the cast diagram, the object is at the center always and to the right horizontally. Moving on to the work done by frictional force, identifying theta for the work done by frictional force. Remember, the frictional force is defined as a force that opposes the motion of an object. And on the cast diagram, the object's motion is to the right. So opposing that motion simply means we are going to the left. There's an angle of 180 degrees, if you can notice. Now the object is going to the left horizontally. Direction of motion is to the left. Direction of applied force is to the left. On the cast diagram, the object is at the center, going to the right, always. So the applied force is to the same direction as the direction of motion, but the frictional force is opposing the motion. So going straight to an angle of 180 degrees. The work done by frictional force is WFF equals FF delta X cosine of 180 degrees. Another scenario, an object is going up an inclined plane. Direction of motion is up and incline. Direction of applied force is up as well, but the frictional force opposes the motion, remember. So on the cast diagram, the object is always at the center, moving to the right horizontally. The applied force and direction of motion are to the same direction, but the frictional force is opposing the motion, going straight to an angle of 180 degrees. The work done by frictional force is WFF equals FF delta X cosine of 180 degrees. Now the object is being pulled to the right at an angle of 15 degrees. The direction of motion is to the right. The direction of applied force is somehow to the right, although it's at an angle. On the cast diagram, the object is at the center, moving to the right horizontally. The applied force is towards an angle of 15 degrees, but the frictional force is opposing the motion, meaning going to the left, straight to an angle of 180 degrees. So the work done by frictional force is WFF equals FF delta X cosine of 180 degrees. Remember, I said the frictional force is opposing the motion, not the applied force. There are cases where the frictional force and applied force are to the same direction. Like in the cases when we are taking a trolley, for example, down the incline. Of course, you are not going to push on the trolley, but be pulling it towards you so that you control its speed or its motion. So in that case, the applied force is also opposing the motion, just like the frictional force, because the object is going down the incline. While the object is going down the incline, you are pulling it towards you, and then the frictional force is also opposing the motion. So in that case, both the frictional force and the applied force are to the same direction. Like in the given scenario, the object is going down an incline, the applied force is going up, and the frictional force is going up. So on the cast diagram, the object is at the center, going to the right horizontally. So both these forces are opposing the motion. So the applied force is to the left and the frictional force is to the left as well. Both the applied force and frictional force are going straight to an angle of 180 degrees. So the work done by applied force in this case is WFA equals FA delta X cosine of 180 degrees. And the work done by frictional force is WFF equals FF delta X cosine of 180 degrees. You have to take note of the fact that even for the frictional force, theta is not always 180 degrees. But in most cases, theta for frictional force is 180 degrees, but not always. Like in the case when the object is being lifted up and the air is blowing at an angle. So in that case, frictional force is the air resistance. So when the air resistance or when the air is blowing on an object at an angle, theta for work done by friction is no longer 180 but 180 minus whatever angle with which the air is blowing an object. Like in the scenario, the hot air balloon is being lifted up, the air is blowing at an angle of 30 degrees. So theta for work done by frictional force will be 180 minus 30 degrees. So the work done by frictional force is WFF equals FF delta X cosine of 150 degrees. That is 180 minus 30 degrees. Now with the work done by gravity, theta is very different, especially on an inclined plane. But remember, firstly, that the work done by gravity on the horizontal surface is 0 joules. Because on the horizontal surface, the force of gravity is acting perpendicular to the surface, making an angle of 90 degrees. Cosine of 90 degrees is 0. Making the whole expression 0. So the work done by gravity on the horizontal surface is 0 joules. But when the object is going up an inclined plane and when the object is going down the inclined plane, so when the object is going down an inclined plane, the work done by gravitational force is no longer 0 joules. And even when the object is going down the inclined plane, the work done by gravity is not 0 joules. So going to the cast diagram, the object is at the center. If you look at 90 degrees is an angle at the top and 270 is an angle at the bottom. So with and only with the inclined plane, theta for work done by gravity is identified as follows. So when the object is going up an inclined plane, you're gonna say, remember the number at the top is 90 degrees. So you're gonna say 90 degrees plus the angle of inclination. And then when the object is going down an inclined plane, remember an angle at the bottom is 270 on the cast diagram. So you're gonna say 270 degrees plus angle of inclination. That's how we identify theta for the work done by gravity, only on the horizontal surface. So now an object is going up an inclined plane, the angle of inclination is 30 degrees. Now when the object is going up an inclined plane, remember an angle at the top is 90 degrees. So the work done by gravity would be WFG equals mg delta x cosine of 90 degrees plus the angle of inclination is 30 degrees. So it's 90 degrees plus 30 degrees because the object was going up an incline. Now the object is going down the incline, the angle of inclination is 35 degrees. So when the object is going down the incline, remember an angle at the bottom on the cast diagram is 270. So the object is going down the incline, meaning theta for work done by gravity is 270 plus the angle of inclination, so 270 plus 35. So the work done by gravity is WFG equals mg delta x cosine of 270 plus 35. Now the object is going down vertically, so the free body diagram will have the frictional force going up, or the air resistance, and then the applied force on the scenario is going down vertically also. Fg is always down vertically, remember. So you could see that the direction of motion is down vertically, frictional force is opposing the motion as always, and then the applied force and the gravitational force are to the same direction. So on the cast diagram, the object is always at the center, moving to the right horizontally. Going back to the scenario, remember both applied force and gravitational force were to the same direction as the direction of motion and were parallel to the direction of motion. So even on the cast diagram, applied force and gravitational force must be parallel to the direction of motion. So applied force is going straight to an angle of 0 degrees. Also the gravitational force is going to an angle of 0 degrees. Frictional force is opposing the motion, going straight to an angle of 180 degrees. So in this case, work done by gravity has an angle of 0 degrees. So work done by gravity is WFG equals mg delta x cosine of 0 degrees. I'm sure your teachers are using, for the work done by gravity, are using mg sine theta delta x cosine of theta. That's fine. You can choose between the two, whichever you prefer, mg delta x cosine of theta or mg sine theta delta x cosine of theta. They are both correct. And again, the work done by gravity can be written as W equals negative change in gravitational potential energy. So WFG equals minus change in EP. That's very useful in some cases. Moving on to energy. Energy is also measured in joules, and energy is a scalar quantity. Remember in grade 1, we were taught that energy is an ability to do work. So I'm gonna be talking about two energies, the kinetic energy and I'm gonna be talking about three energies: the kinetic energy, the gravitational potential energy, and the mechanical energy, being the sum of these two energies, kinetic and gravitational potential energy. So kinetic energy is the energy an object has due to its motion, and then the gravitational potential energy is the energy an object has due to its position above the Earth's surface. Mechanical energy is the sum of kinetic energy and the gravitational potential energy, or the sum of gravitational potential energy and the kinetic energy. Kinetic energy is EK, or K equals half mv squared. Gravitational potential energy is EP equals mgh. So in the kinetic energy, V is the velocity, and then in the gravitational potential energy, H is the height above the Earth's surface. Not just any height, but height above the Earth's surface, above the horizontal Earth's surface. Mechanical energy is Emech equals U plus K, or EP plus EK. So when the system is isolated, the mechanical energy is conserved. And that brings us to the principle of conservation of mechanical energy, which states that in an isolated system, the total mechanical energy remains constant or is conserved. So mathematically, Emech before, meaning at point A, equals Emech after, meaning at point B. So Emech, remember, can be expanded to U plus K, the gravitational potential energy plus the kinetic energy. So U plus K before equals U plus K after. Also, U can be expanded to mgh K 1 over 2 mv squared. So we're gonna have mgh plus 1 over 2 mv squared equals mgh plus 1 over 2 mv squared for the conservation of mechanical energy. The mass is of the same object. Remember, this is the same object moving from point A to point B. So they might not give you the mass of an object and ask you to calculate maybe the velocity or the height. It doesn't matter whether or not you are given the mass, because anyway the mass is of the same object. So on the left side of the equation, m is common. Even on the right side of the equation, and m is common, so m can cancel out. So it doesn't really matter whether or not you are given the mass of an object. So in this chapter we have two energy principles. The first one is the principle of conservation of mechanical energy. The second one is the work energy theorem. Work energy theorem is also an energy principle. The work energy theorem states that the work done on an object by the net force equals the change in object's kinetic energy. So mathematically speaking, the work energy theorem is W net equals change in EK. Remember, work net is the work done by force 1 plus work done by force 2 plus work done by force 3, depending on the number of forces doing work. And also remember, change is final minus initial. So change in EK is 1 over 2 mv squared minus 1 over 2 mvi squared. So the final and the initial kinetic energy. So these two formulae, the principle of conservation of mechanical energy and the work energy theorem, can be used depending on the given information. So when the given information allows you to use work energy theorem, use work energy theorem to calculate whatever. When the given information allows you to use the principle of conservation of mechanical energy, use the principle of conservation of mechanical energy. But when they said use work energy theorem, now they are specific. They want you to use work energy theorem and only work energy theorem. Work energy theorem is also called work energy principle. So there's energy principle, there's work energy principle. Work energy principle is work energy theorem. So in this chapter, forces can be classified as being conservative forces and non-conservative forces. An example of a conservative force is the force of gravity and the ones listed. The example of a non-conservative force is the frictional force and the ones listed. So in the presence of a non-conservative force, the mechanical energy is not conserved. So once there's a non-conservative force, the mechanical energy before is no longer equals the mechanical energy after. So Emec before is not equals Emec after. So that goes down to the work done by non-conservative force being the change in the kinetic energy plus the change in the gravitational potential energy, or U plus K before plus work done by non-conservative force equals U plus K after. You can use whichever formula you prefer to calculate either the work done by a non-conservative force or a non-conservative force itself, or whatever between the height and the velocity. I'm not gonna stress much on power. Power is the rate at which work is done, measured in watts. Power can be calculated using P equals W over delta T. P is the power, W is the work done by whatever force we are calculating its power, or power it wasted if that's the case, and then delta T is the time in seconds. So when you are given a constant velocity, you can use P equals FV, V being the constant velocity. So another thing, make sure you take note of these two words, constant velocity. Constant velocity, remember in Newton's laws, Newton's second law, when an object is traveling at a constant velocity, the object has an acceleration of 0 meters per second squared. When the acceleration is 0 meters per second squared, F net is 0 newtons. When F net is 0 newtons, work net is 0 joules. So in this chapter, when an object is moving at a constant velocity, that simply means the work net is 0 joules. Thank you very much. So for more information, please go through your notes, textbooks, consult with your teachers.